Hello everyone. So this video is going to be dealing with properties of exponents. So basically we're going to be working through the logic of how exponents work. So we're going to start with, what do exponents even mean? Let's just look at our first example, 7 to the 4th power. So what exponents tell us are this number times itself this many times. So 7 times itself 4 times. So we have 7 times 7 times 7 times 7. That's what exponents mean. We don't always want to write 7 times 7 times 7 times 7, or say it for that matter. So we're just going to write 7 to the 4th power. It's an easier way to write math. Let's look at x to the 5th. The 5th power says we're multiplying x times itself 5 times. So it's x times x times x times x times x. Just a simpler way to write it is x to the 5th. Alright, now let's start to get into our properties. So if I have 7 squared times 7 to the 3rd power, well, this 7 squared is just like saying 7 times 7. And this 7 to the 3rd power is saying 7 times itself 3 times. Notice that there is multiplication going on inside of here. So altogether, we have 7 times itself 5 times. So simplified, this could be 7 to the 5th. Okay, let's try another with a variable. So we have x to the 4th times x to the 3rd. This is saying x times itself 4 times. And x to the 3rd is saying x times itself 3 times. Notice that again, there's multiplication in between there. Multiplication in between. So all these x's are being multiplied together. So in the end, we have x times itself 7 times. So this is x to the 7th. Now let's just look at these examples. Here we have 7x squared, or excuse me, 7 squared and 7 cubed. Their powers added together equal the end result. Here, with the same base of x, add their exponents together and you get the end result. So the rule is, if your bases are the same and being multiplied together, take the first exponent, add it to the second exponent, and that's going to be your result. Okay? Now let's keep on working with this kind of multiplication rule. So here we have 5 to the 4th, and that whole quantity is squared. So we can think of this 5 to the 4th as some blob, as something. Something to the 2nd power is that same something times itself twice. So blob times a blob. So a blob times another blob. Because of that 2, we're writing 2 blobs. Well, what is the blob? Blob is 5 to the 4th. So inside I have 2 5s to the 4th. 5 to the 4th, 5 to the 4th. What does 5 to the 4th really mean? Well, it's 5 times 5 times 5 times 5. That was the first blob, and here's another blob. 5 times 5 times 5 times 5. Now all these are being multiplied together. So how many 5s do we have multiplied together? Well, we have 8. So this is really 5 to the 8th. Okay? Let's try another one with this blob. So we have x to the 3rd to the 4th. So we have this blob multiplied by itself 4 times. So 1 blob, 2 blob, 3 blob, 4 blob. What is the blob? Well, x to the 3rd is the blob. So x to the 3rd is in each of these parentheses. And what does x to the 3rd mean? Well, it means x times x times x. And each of these is that x times x times x. And in the end, we want to see how many x's do we have altogether, because they're all being multiplied together. So we have 3, 6, 9, 12. So in the end, we have x to the 12th power. Okay? Let's try another one. Now we have 2 different variables. So I have this blob, and this exponent says, do that blob, multiply it by itself 3 times. So 1 blob, 2 blob, 3 blob. And inside the blob is xy. Oops, broke my lid. So the parentheses are saying multiplication. The space, there is no symbol in between the x and the y, so that means multiplication. So all these are being multiplied together. So how many x's are being multiplied together? 1, 2, 3. So this is like x to the third. And then we have y times y times y, 3 of them, so that's like y cubed. Now notice, the x's aren't next to each other, nor are the y's, but multiplication, it does not matter the order. All it matters is that they're still being multiplied together. So order doesn't matter. If the x's were all the way on the other end, I still could do this. They don't have to be next to each other to be combined like this. So our end result, x to the third times y to the third. One more. So here we have a squared times b to the third. Sorry if that looks kind of nasty. My pen went astray there. So this is a squared times b to the third. That whole quantity squared. So something squared is something times itself twice. And what's inside the blob is a squared times b cubed. A squared b cubed. So we can break these up. So you have a times a, b times b times b, a times a, b times b times b. So how many a's do we have multiplied together in the end? We have 4, so that's a to the fourth. And then b, we have 6 of them, so oops, b to the sixth. So let's take a look at how these powers came about. So here we had 5 to the fourth, and then we had that squared, and it resulted in 8. To the third, that whole thing to the fourth, 12. This was to the first, to the third, and these came out to the third. This was to the second, came out to the fourth after being squared. The third came out to be a 6 after being squared. So what we're noticing is multiply the exponents to get your end result. 4 times 2 is 8. 3 times 4 is 12. 3 times 1 is 3. 3 times 1 is 3. 2 times 2 is 4. 2 times 3 is 6. So the general rule, a to the m, that whole quantity to the n power, is a to the m times n power. So now you're multiplying the powers together. Okay? Let's look and see how that applies when we deal with fractions. So it's going to be the same thing. We have some blob to the third power. So we have that something times itself 3 times. So that something, that blob, is 2 to the fifth. And what we know about fractions is we can multiply their numerators together, multiply their denominators together to get the end result. Well, 2 times itself 3 times, that's 2 to the third. 5 times itself 3 times is 5 to the third. So this is our end result. We're not looking for the actual value, we just want to put it in exponent form. Alright, we want to just look at their properties, so that's all done. Here's another one with variables. We have x divided by y to the fourth. So blob to the fourth is that blob times itself 4 times. So in that blob is xy, x over y, excuse me. And again, fractions multiply their numerators, so x times itself 4 times is x to the fourth, y times itself 4 times is y to the fourth. That's our end result. Here's a little bit trickier one. So we have this blob, 6z over 4b squared, and that whole quantity is squared, so that blob is being multiplied by itself twice. So 2 blobs there. Inside the blob is 6z over 4b squared, 6z over 4b squared. So multiply your numerators. So we have a 6 times a 6. 6 times itself twice is 6 squared. Z times a z. Z times itself twice is z squared. 4 times 4. 4 times itself twice is 4 squared. And b squared times b squared. So let's go back and look at our previous rule over here. 7 squared times 7 cubed was adding the powers together. So if we have b squared times b squared, we're going to add the powers together. So this is b to the fourth. So this big messy thing, when broken down, is going to look like this. So the rule that we're seeing here is we had a fourth power, and in the end, x was to the fourth power, and so was the y. In the end here, the 2 was to the third power, and so was the fifth. Same thing with all these. The 2, all these were to the second power. the 4. The b looks a little bit different, but it's the same thing. So the rule is a over b, that quantity to the m power, is just saying like a to the m divided b to the m. So the power goes to each of the parts of the fraction, the numerator and the denominator. Okay? We're going to continue working with fractions right now. So let's say we have 2 to the 8th. 2 to the 8th is broken up 2 times 2 times 2 times 2. That's 4, 5, 6, 7, 8. Oof. I'm so glad we have exponents because I don't want to write that every time. That's all over 2 to the 5th, which is 2 times itself 5 times. Oops, 2. Now, looking at this, we see that the top has some of the same factors as the bottom. I can pull out a 2 from the top, and I can pull out a 2 from the bottom, and they reduce to just 1. So they're gone. The same thing can happen with the rest of these. As long as the 2's have a match, they can be reduced because they're a factor of the bottom, of the denominator, and of the numerator. There's no addition going on, so it's all multiplication, so they're all factors. So what are you left with when you reduce all that? You're left with 2 times itself 3 times, which is 2 to the 3rd. So 2 over to the 8th over 2 to the 5th is really just 2 to the 3rd. Okay, let's try that again with some variables. Here we have a to the 6th, so a times a times a times a times a times a over a times a. So here we see that these a's reduce, and we're left with 4 of them. So a to the 4th is the simplified version of a to the 6th over a to the 2nd. So if we look at this, we have the 8th power and the 5th power, and we end up with the 3rd power. We have the 6th power and the 2nd power, we end up with the 4th power. The rule is subtract your powers when dividing to get the new power of the new exponent of that same base. So 8 minus 5 is 3, 6 minus 2 is 4. Okay? So if you have something a to the m over a to the n, notice the same bases. The same bases of 2 and 2, a and a. That result is that base to the m minus n power. So here's a neat little connection. Notice we're dividing here and we're subtracting our exponents. Here we're multiplying and we're adding our exponents. So it's the opposites. Okay? Now let me change papers here, and we're going to use that rule we just learned. Okay? So first we're looking at 2 to the 3rd over 2 to the 5th. So we're going to do this just like we did before. We have 2 to the 2 times 2, and 2 to the times 2 times 2 times 2 times 2. Oh my gosh, that's a lot of 2's. So reduce what you can with the numerator and the denominator. What are we left with? We're left with 2 times 2 on the denominator, which is 2 squared. And on the numerator, remember there's always that multiple of 1 hidden out there. So it's not 0 on the top, it's 1. So 1 over 2 to the 2nd. But wait a second, we have that new rule we just learned. That new rule stated, take the degree of the numerator and subtract it from the degree of the denominator. So this should be equal to 2 to the third power minus 5. So if I do that, that's 2 to the negative 2. So these are equal according to our rule and our logic of pulling out factors. So let's do another problem to see what that looks like. Here we have variables. So x to the 5th, x times itself 5 times, over x to the 8th. So if we reduce our x's, we have 3 left over in the denominator, so that's x to the 3rd, and remember that we had that hidden 1, so this is over 1. But let's use our rule. Our rule again says if they have the same base, you can subtract their powers. The numerator minus the denominator's power. So this is really x to the negative 3. Interesting, huh? So these must be equal. Well, let's see what else we have planned. We have 3 to the 5th over 3 to the 5th. So that's 3 times 3 times 3 times 3 times 3 over that same thing, 3 times 3 times 3 times 3. Well, if we reduce all of our factors, we're left with nothing? Well, remember we have that hidden multiple of 1 there, so it's not just nothing, it's actually 1 over 1, which is 1. But again, let's use that rule that we just learned. 3 to the 5th minus 5, the numerator power minus the denominator power, which gives us 3 to the 0? Okay, well, I can see that there's a 3 and a 3 here, and a 2 and a 2 here, so the powers look the same, there's just this negative, but there is nothing that's the same right here. Absolutely nothing. So maybe we need another example, because these things are supposed to be equal. Let's try x's. X's are always helpful. So x times x, because we have x to the third, x times x again, because it's x to the third again. They all reduce, so again that hidden 1 is there, and this is just 1, just like the last one. Using our new rule, x to the third minus 3, well, that's x to the 0. Well, the only pattern I'm really seeing here is something to the 0 power, and that turns out to be 1. That is the rule. Anything to the 0 power is 1 because of this. You have the same exponent in the numerator and the denominator, and when you subtract those using this method, something to the 0 power is always going to be 1. They're all going to reduce with each other, so it's always 1. A to the 0, anything to the 0 power is 1. And looking back up at this rule, we see that we have x to the negative third. That turned out to be 1 over x to the third. Here we had 2 to the negative 2. That was 1 over 2 to the 2. So what our pattern looks like when we have a negative exponent, we're just going to take that and put it into the denominator. So a to the negative n is 1 over a to the n. So we're just getting rid of the negative and putting it in the denominator. But not just the denominator, which we're going to see in a little bit. It's actually just flipping it. So if it's in the denominator, it's going to move to the numerator. If it's in the numerator, it's going to move to the denominator. But we'll look at that in a little bit. For right now, let's take a peek at this table. So here we have a table of base 3. 3 to the 4th is 81, 3 to the 3rd is 27, 3 to the 2nd is 9, 3 to the 1st is 3. Let's just keep on completing this table, starting with our bases of 3. So we started with 4, worked our way down to 3, to 2, to 1. So this is going to be 3 to the 0. With the knowledge that we now know, anything to the 0 power is 1. Okay. Moving down another step, 3 to the negative 1. Our rule now states anything to the negative power is that same power, but now it's in the denominator. So we're going to do 1 over 3 to the 1st. And 3 to the 1st is just 1 over 3. Alright, keep on working our way down. So 3 to the negative 2. Our rule states flip it and keep that same power. So 1 over 3 to the 2nd. Well, 3 times 3, that's 1/9. And let's do it one more time. 3 to the negative 3rd. Well, that's 1 over 3 to the 3rd, which equals 3 times 3 times 3, which is 1 over 27. So sorry if those numbers are kind of small, but let's look at this. We have 1 over 3 when it's a negative 1 power. When it's a 1 power, we just have 3. When we have 3 to the negative 2, it's 1 over 9. When we have 3 to the 2, it's 9. When we have 3 to the negative 3rd, it's 1 over 27. 3 to the 3rd is 27. So what you should be seeing is that when you have a negative power, it's actually the reciprocal of the positive power. So 3 to the third was 27 over 1. 3 to the negative third is 1 over 27. So the biggest thing you need to know is look for this, you see this pattern. It's that reciprocal going on. So if it's in the numerator, it's going to move to the denominator. If that negative is in the denominator, it's going to move to the numerator. So just a quick recap, a to the negative 2, we're going to flip it into the denominator. If we have 1 over b to the negative 2, we're going to flip it to the numerator. So the reciprocal we're looking at, and you could actually write this as just b squared. This guy, 3 to the fourth, that's positive, and there is no other 3's in here, so there's nothing we can do with that one. But c to the negative fifth, that means do the reciprocal. So 1 over c to the positive 5. Now notice that this 3 to the fourth, that's actually over 1. And this is being multiplied, so we can multiply numerators by and multiply denominators. So you could simplify this to 3 to the fourth over c to the fifth, which we would like you to do. Notice that there's no negative exponents and nothing that is the same is running around. Everything is combined as clean as it can be, as concise as it can be. Okay. So here we have m to the third and m to the negative 2. M to the third, we're just going to leave that alone. But we know m to the negative 2, when we see that negative power, we're going to do the reciprocal. So that means, if we want to, we could break this down a little bit. This is m to the third over 1 times 1 over m to the negative 2. If you multiply the numerator, multiply the denominators, you're going to get this back out. But it lets us see this reciprocal action happen. So the reciprocal of m to the negative 2 is m squared over 1. Now you can see that there's two m's, two things with base m, and when we multiply together, our rule says add the powers. So m to the fifth is our answer. Okay, one more, actually two more, I lied. Here we have a whole something to the negative 2 power. Well, what we saw on the previous page was that quantity to a power is just saying everything inside to that power. So it's like we're distributing this negative 2 to each thing. So 4 to the negative 2 over 5 to the negative 2. If you want to break that out so you can see the reciprocal action, you can put it over 1. Broke my lid again. 1 over 5 to the negative 2. Negative 2. Oops, multiplication there. So do the reciprocal action. This is going to move it to the denominator. Now it's a positive exponent. This is going to move it to the numerator. Again, positive exponent now. And when you multiply that, numerator times numerator, denominator times denominator, and that is that. Okay, one more. This one has variables, so we're going to distribute this negative 3 to each one. So x to the negative third over y to the negative third. You want to see that reciprocal action really happen, you can break it up, or you can just skip to the final step, which is flip them, change their exponents to positive, and then put them back together. Okay. So the rule for the negative exponents, really quick, is a over b to the negative m power. It's just saying, okay, flip that fraction and distribute that m. So we flipped it, so now it's b over a, and each thing is being multiplied by m. Okay, so just a quick recap of the rules. First one is when we have the same base being multiplied together, we add the powers. Down here, we have a to a power, that whole quantity to another power, and the result, you multiply the powers together. If you have a fraction, to a power, you're going to distribute that fraction to each of the bases. So it's a to the m over b to the m. If you're dividing with the same base, you subtract the powers. Anything to the 0 power is 1. Something to the negative power, you do the reciprocal. And lastly, if you have a fraction to a negative power, you do the reciprocal and then distribute that exponent through. So this has been a review of the properties of exponents.